Professor of Geology at the University of Tasmania, Ross Large. He's the CEO of CODES, the Centre of Excellence in Ore Deposits, a world leader in ore deposit genesis, exploration and metallurgy. Ross certainly struck me as a really good bloke, down-to-earth, serious geologist. Ross actually has a live mandate, as Ed had mentioned, with DGO and maybe other companies presenting today. Ross, looking forward to hearing what you've got to say.
I thought I'd take up the challenge of the theme that you've presented to us. It's a while since I've been disco dancing, but I can always dream about it. Can everyone hear me okay?
Yeah, and look at $1 million in your velour purple suit there, Ross. Nice one.
Yes. Afraid it doesn't fit anymore. Just for those who don't know me, a bit of my history. I did a PhD at the University of New England under Dick Stanton back in the 1970s. Dick was one of the top global economic geologists at the time, and I learned a lot from him. And then spent 12 years in mineral exploration working with Geochemical. That team was led by John Elliston and was a very successful team in the 60s, 70s and 80s in exploring for a number of deposits, finding the Ranger uranium deposits and many deposits in Tennant Creek and the porphyry deposits in New South Wales. I then went back to university to take on the role of an economic geology teacher, and out of that I developed a research centre called the Centre for Ore Deposit and Exploration Studies, that's CODES, and that became one of the most successful research outfits in mineral deposits, and still is, since I've now stepped down from that role, and David Cook is running the show, doing a great job. And I've now, since stepping down, I've been working as a consultant in the minerals industry. Oh, I can't seem to advance the slide. There we are, down at the bottom. Rightio. Now, in 2014, Ed, the chairman of DGO that you've just heard, asked me for some advice on where to explore for gold and copper in Australia, and especially to think outside the box in this process. And it was fortunate because I'd just been completing a project on developing a new theory for the formation of gold deposits. This was a project that started in Russia, actually, looking at one of the famous deposits, Suko Log, where it was obvious that the deposit formed by quite a different process to the way we've been thinking about gold deposits. And this was a two-process theory that the Russians had actually worked on themselves back in the 60s. And we published this research in economic geology in 2011 and won the best paper award for that. And when Ed asked me, I thought that this is a real chance to apply what we've been thinking of academically into mineral exploration. Now, just to summarise the model that we developed, this two-process model is that, first of all, process one is that most gold is derived from the continents simply by oxidative erosion of the rocks. Very small amounts of gold get into the stream system and into the ocean. And that gold actually circulates around in the ocean for many 100,000 years before it actually is finally deposited in the muds on the ocean floor that turn into what we now call black shales. And the gold is trapped in the pyrite in the black shales. And it can sit there in those shales for many millions of years. And then process two releases the gold. That's a metamorphic event that squeezes the rocks. It actually transforms the pyrite into pyrrhotite. It releases the gold and arsenic and tellurium and a few other elements, and they move up to form the ore deposits that we mine today, especially the orogenic type of deposits. So this is a model of formation of gold in sediment sedimentary basins. And the premise behind this model is that gold is dissolved in seawater for a long period of time. And so we decided that we'd try and measure the amount of gold in seawater through geological time, from the Archean, from 3,500 million years ago right through to the present. We did that by analysing sedimentary pyrite in black shales. Took us a long time to collect enough data. We needed about 6,000 analyses, but you can see here, this is the pattern of gold in seawater through time. It reached a peak around 2,700 to 3,000 million years ago in this position. It had another peak at about 2,600 million. It had another peak at about 2,200. And then it dropped right down for a long time before it peaked at about 1,000 and then at about 600 and gradually declined to the present day. But the interesting thing is that those peaks are times when major gold deposits are formed in the Earth's crust, like the Kalgoorlie Golden Mile at 2,650, and the Witwatersrand Basin, the biggest gold accumulation on Earth, around 2,800. A number of major deposits at 2,200. Interestingly, we don't know of any big deposits at 1,000, but that's an exploration opportunity. But it's no good exploring in this period when there was such a drop in gold in the oceans. We call that the boring billion, when no gold deposits of significance formed in the Earth's crust. And then in the more recent years, 600 million years is a prominent time, and 400 another prominent time. And so we devised a program to look at the Australian geology and try and peg ground of this particular age that had the right rock types. And so GGO pegged about 12 areas at that time. And one of those was in the Pilbara and in the Ballina Basin, which is still being explored today with some success. A number of the other areas proved not to be that successful. But that was how it all started with DGO, and I've continued with them to advise, especially on geochemical techniques. And I just want to emphasise a couple of breakthroughs in geochemical prospecting that are making a big difference nowadays to the exploration by most companies, or by the companies that are advanced in these areas. And the first of these is multi-element soil and rock geochemistry. And this enables us to actually develop the geology of an area from the geochemistry of the soils. It's quite amazing that the advances that have been made in the laboratories now allow us, when you've got a gibber plain like this, which is typical of much of Western Australia, you've got no outcrop, you've got no idea what the geology is, but by just taking a sample at about 30 centimetres below the surface, it gives us very important information about the geology below, which really is not seen until you get down about 50 to 100 metres when the rocks become fresh again. And the real advance is the way the samples are digested, are 4-acid digested, and then how they're analysed by inductively coupled plasma mass spectrometry, which has been around for some time, but the labs have now developed it such that you can get very low level detections of gold and about 30 other elements. And critical elements that are the vector elements, or what we call the pathfinders, like bismuth and antimony and arsenic and thallium for gold, can be analysed very easily at very low detections. And the other elements that are useful are the rock forming elements and the very resistive elements that remain in the soils, even though the rocks have been totally decomposed, such as vanadium and thorium and chromium and lanthanum, scandium, etc. And we can use those to build back the geology of the area, even though it's covered by, in many cases, transported overburden. We can still see through that. This is an example in a DGO area where a standard soil sampling survey has been done over vast gibber plains. And you can see when we look at the lanthanum scandium ratio that there's a rock type in here that has a very high ratio. Now that we know that felsic rocks, in particular rhyolites and dacites, have a very high number. So that is telling us this is probably a rhyolite or dacite sequence. And there's other parts of the area that also have minor concentrations, as you ratio. That tells us about where the mafic rocks are, where the basalts are. And you've got obviously all these highs over here are telling us there's a big pile of basalts buried under there. And we're also seeing other little zones of basalt coming through here. So from that, we can build up the geology. We can build up this big pile of basalts over here. We can suggest that there's another basalt sequence of different nature coming through here. We've probably got a rhyolite in here. So we've got a volcanic center most likely. And then that's where our gold anomaly sits, surrounded by some of the vector elements like thallium and antimony and arsenic, and another one sitting up here. So it's pretty logical. You can roll the drill rig in and drill a hole right through that anomaly and have confidence or relative confidence in the target that you're looking for, because we've got a much better idea of the geology. Now, the other development that's important, and I've had some involvement in, is the use of pyrite chemistry to help vector towards ore deposits. This is another of these ICPMS techniques, but in this case, you use a laser to laser into the pyrite and analyze at very low levels. And it's particularly useful for gold exploration, but also relevant to other types of deposits. And that's because the pyrite traps gold, silver, and a whole range of other elements in its structure, and it amplifies them to give you a much stronger signal. Now we can map the pyrite with our laser system. And this is a bunch of pyrites from a black shale in an environment where there's sedimentary copper deposits. And you can see here that these pyrites, which don't have much cobalt in the center of them, have got a rim of cobalt. If we go to copper, you can see the same. We've got a rim of copper. That's telling us that the fluid that's coming through those shales is transporting and depositing cobalt and copper and a little bit of zinc also. Now that's really important information. And in the case of a case study we did in the Stewart Shelf, again for DGO, we found that although this is a copper cobalt corridor, the pyrite was enriched mainly in silver. These pyrites are extremely interesting. They're fine-grained, what we call framboidal pyrites with a star cluster surrounding them. The laser blows into those and just demolishes them, and the material that comes off is fed into the mass spectrometer, and we analyze it, and it turns out that these are quite silver-rich, and the amount of silver increases as you get close to where the major centres of mineralisation are. So from that, we've got centres of mineralisation down here at Mile Creek and Mount Gunson and Emmy Bluff. And these new highs that we found are indicative of potential new ore deposits sitting close into these areas. And this is one of the areas that DGO is currently exploring in detail on the Stewart Shelf and having some success. We called this the silver bullet for mineral exploration for sedimentary copper deposits, because the silver is such a good indicator of proximity to ore. Well, I think I've probably run out of time now, so I'll leave it open for any questions. Thanks very much.
Ross, love your work, mate. The silver bullet. Hopefully that